Hello and welcome to this lesson for OCR A-Level Physics, Module 6, Particles and Medical Physics, in the topic of electrical fields and looking at the concept of electrical potential. So if we've been successful and we've learnt in today's lesson, we should be able to define absolute electrical potential, detail the properties of electrical potential in an electrical field, and consider the concept of when work is done in an electrical field. Now, in the previous lessons, we have considered electrical fields. Now, the existence of an electrical field indicates that an object has charge. Now, through Coulomb's law, we've considered the force exerted on two charged objects due to their interacting electrical fields, whilst the field strength details how much force per unit positive charge will be exerted on an object due to being placed there. Now, we can consider an object to also be a store of electrical potential energy when found inside an electrical field. So there must be another factor we can consider, the energy stored in an object due to being in an electrical field. So this concept is called the electrical potential. So the potential details the energy stored in one object per unit property of the field due to the object being in the field. And this is due to the field that is produced. Now, an example of this is the gravitational potential, which is the gravitational potential energy per unit mass experienced by an object inside a gravitational field. So if we consider an electrical field produced by a positive charge, remember the standard derivation of electrical fields favours the concept of using positive charge. So all electrical field notations use positive charge. Now, any other charged object placed inside the electrical field will become a store of electrical potential energy. Now, this electrical potential energy store is produced because of a resultant electrostatic force acting on the object due to being in the field. Now, this energy is due to the attraction or repulsion produced between the charges. Now, in general, work must be done to move a charged object towards another object that has the same charge. Their electrical potential energy increases as they move towards the object. So their electrical potential energy increases from zero as they move towards the object from infinity, which we define as outside the field. So the electrical field of the stationary object causes a force of repulsion on the object which is moving. So this force must be overcome to move the objects closer to each other. So this gives us the concept of absolute electrical potential. This is the electrical potential energy stored per unit positive charge due to being placed at a point in the electrical field. Now we give this quantity the symbol V. Now we can set the absolute electrical potential to be zero at any place, however we choose to set it at infinity. Now we define infinity as any region outside of the electrical field. Now, we set infinity to have zero absolute potential as the particle is outside of the field, so feels no force from the field, and it is no longer an electrical potential energy store. So we can summarize this with the following graph. So what we can say is that the electrical potential is equal to zero at infinity, very, very far away. Now, the test charge would normally move towards a negative charge due to electrostatic attraction. So therefore this would decrease our absolute electrical potential. But work needs to be done to pull the positive test charge away from the negative charge, so it would increase the electrical potential. So as we can say, the electrical potential V decreases in the direction the test charge would naturally move in due to attraction or repulsion. Now we can calculate the absolute electrical potential with the following equation, that absolute electrical potential is equal to the electrical potential energy stored divided by charge, or V is equal to E over Q. Now this equation comes from the definition of absolute electrical potential, and this gives the units of our absolute electrical potential to be joules per coulomb. Now this is also the same as the volt, so 1 volt is equal to 1 joule per coulomb. Now this makes sense as the definition of potential difference from the module electricity is the work done per unit charge, and this is very similar to the definition of absolute electrical potential. Now the unit of potential difference is also the volt. So therefore, if the charge in the field is positive, this would make the electrical potential also be positive, as there is repulsion. So it means that if the charge starts off close to the charge making the field and moves away, the potential tends to zero as the charged object moves to infinity. Whilst if the charge in the field is negative, then the electrical potential is negative as it is attracting. Now, if the charge starts off far away from the charge making the field and moves closer, this means the potential tends to infinity as the charged object tends to zero. So these definitions lead to the following graphs. So this is a graph which shows how the electrical potential of an object changes with the distance from the charged object producing the electrical field. So we can consider this part of the graph to be when the object in the field is experiencing a repulsive force. And this part of the graph shows when the object in the field is experiencing an attractive force. So with repulsion, it starts off as positive, and as the distance increases, it tends to zero, but always stays as a positive value. So as a reminder, this is for positive charges. Whilst on the other side, we start with its attraction, it starts off as negative, the distance increases and it tends to zero, but it always stays negative. And this is for our negative charges. So we can summarize it again with the following graph. The values for V are all negative for a negative charge. The values for V are all positive for a positive charge. As R increases, V against R follows a 1 over R relation for a positive charge and a minus 1 over R relation for a negative charge. The gradient of the graph at any particular point is the value of E, the electrical field strength at that point, and our graph will show a shallow increase or decrease as R increases. Now we can also calculate the absolute electrical potential for a radial field with the following equation. V is equal to Q over 4 pi epsilon 0 R. But this equation is only applicable to radial fields. Now remember that the field strength and force are related to the separation from the charge by the term 1 over r squared, but energy and potential are related to the separation by the term 1 over r. Now we can derive this equation as we know the work done per charge is equal to the force per charge times by the distance. Therefore, multiplying the electrical field strength by the distance gives the electrical potential. So if we say work done per charge equals force per charge times by distance, we can say V is equal to E times by D, where E is equal to Q over 4 pi epsilon 0 r squared times by r, so it equals to Q over 4 pi epsilon squared r. So therefore, we can say multiplying the electrical field strength by the distance gives our electrical potential. Now, we can also say that because the field strength and force are related by the separation of the term by the 1 over r squared, this is an inverse square relationship. Whilst because the energy and potential are related to the separation by the term 1 over r, this is an inverse proportional relationship. Now we can also use the principle of dividing the electrical field strength by the distance to find the electrical potential for uniform fields. However, this gives us the startling conclusion that if E equals V times by D, and therefore V equals E times by D, we can therefore say it equals V over D times by D, so we're saying V equals V. Now we can also link this back to our absolute electrical potential, which is electrical potential energy over charge, as this equation can be used for any electrical field. So this tells us we can interchange these equations if the field produced is radial, which is produced by a charged sphere. Now this can be useful when deriving values in questions, but please be aware that the electrical potential is a vector, whilst the electrical potential energy is a scalar. Now, electrical potential is defined as a positive when showing repulsion and a negative when showing attraction. So the vector quantity in electrical potential comes from the charge aspect of the equation, whilst the electrical potential energy is a scalar term as it's stored in the object. There's no direction to the energy stored in an object. Now, as electrical field strength and electrical potential are vectors, we can use this to determine resultant values when there are multiple charges present. This can be easily determined for a point between two charges, because if you want to work out the resultant electrical field strength at a point x between the two objects, you must carry out the following. Work out the electrical field strength at point x from charge A. Work out the electrical field strength at point x from charge B. Sum the two values, but beware it's likely that they're acting in opposite directions, so this will in fact be a subtraction. Now again, if you wanted to work out the resultant electrical potential at point x between the two objects, you carry out the following. Work out the electrical potential at point x from charge A. Work out the electrical potential at point x from charge B. Sum the two values, but once again, beware it's likely they'll be acting in opposite directions, so they'll be subtracted. So for example, in this following scenario, work out the electrical field strength at point x. Well, from charge A, it's E is equal to Q over 4 pi epsilon 0 r squared. So it's 4 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.45 squared, which is 177.6 newtons per coulomb to the right. We then work out the electrical field strength from charge B. 1 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.30 squared, which is 99.9 newtons per coulomb to the left. As one is acting to the right and one to the left, we can then sum them, which is actually a subtraction, so it's 17.7 newtons per coulomb to the right. And we can also, for the same situation, work out the electrical potential at point X. So you can work it out from charge A, where V equals Q over 4 pi epsilon 0 r, so 4 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.45, which is 79.9 volts. We can then work out the potential from the electrical potential from charge B. So it's minus 1 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.30, which is minus 20 volts. The resultant, again, is the two summed, which is the subtraction, so it's plus 59.9 volts. Now again, we could work it out of the two positive charges. So again, you would work out your electrical potential from charge A, which is 79.9 volts, and this time work out the electrical potential from charge B. But now it's positive 20 because it's a positive charge, so therefore all positive charges produce positive potentials. So you sum them, which is now an addition, so it's plus 99.9 volts. Now we can also determine the actual electrical field strength or electrical potential at a point at right angles between two charges. So if you wanted to work out the resultant electrical field strength or electrical potential at point X between two objects, you must carry out the following. Work out the electrical field strength or potential at point X from charge A. Work out the electrical field strength or electrical potential at point X from charge B. Sum the two values by using the Pythagorean theorem. So, for example, in this situation, how do you work out the electrical field strength at point X? Well, you work out the value of the electrical field strength due to charge A. So E equals Q over 4 pi epsilon 0 r squared. So you work that all through to be 899 newtons per coulomb upwards. Whilst from charge B, we can see that E is equal to Q over 4 pi epsilon 0 r squared, so you work it out to be 99 newtons per coulomb to the left. Now our resultant is due to the Pythagorean theorem, the resultant is equal to 899 squared plus 99 squared, all square rooted, is 904 newtons per coulomb. Whilst our resultant angle is tan is equal to opposite over adjacent, so it equals 84 degrees. So to summarise what we've learnt in today's lesson, we can understand the definition of absolute electrical potential, including the zero value at infinity, and an understanding of electrical potential difference. We also can understand that the work done in moving charge Q is given by the equation that the work done is equal to Q times by delta V. So, if we've been successful and we've learnt in today's lesson, we can define absolute electrical potential, detail the properties of electrical potential in an electrical field, and start to consider the concept of when work is done in an electrical field. So thank you so much for watching this video for OCR A-Level Physics in Module 6 Particles and Medical Physics in the topic of electrical fields, looking at the concept of electrical potential. Thank you so much and have a lovely day.